Imagine you are standing on the edge of the Earth, at the highest point you can find, and you look up into the night sky. You see thousands of stars scattered across the darkness like tiny diamonds thrown onto black velvet. Each one of those stars is a sun, just like ours, burning with unimaginable fury, fusing hydrogen into helium, pouring light and energy out into the cosmos. And the closest one, the very nearest star to our own sun, is a small, dim reddish star called Proxima Centauri. It sits just 4.25 light-years away from us. Just 4.25 light-years. That sounds close, doesn't it? It sounds like something we should be able to reach. After all, we have built rockets that have left our solar system. We have sent probes to every planet. We have landed machines on Mars, flown past Pluto, and even touched the Sun. Surely, we can cross a measly 4.25 light-years. But here is where the story takes its first dark turn, because before we can even think about reaching another star, we need to answer a much more fundamental question. A question that sounds so simple, so innocent, that you might think the answer would be easy. How many years would it take humanity to cross just one light-year? Not 4.25 light-years. Not the distance to Proxima Centauri. Just one single light-year. And I promise you, by the time we are done here today, the answer to that question will change the way you look at the night sky forever. But before we dive in, let me tell you what we are going to explore today, because this is not going to be a surface-level discussion. We are going deep. We are going to first understand what a light-year truly is, and I don't mean just the textbook definition. I mean, we are going to feel it, viscerally, in our bones, until the scale of it makes your stomach drop. Then we are going to look at every fast thing humanity has ever built. From the fastest car, to the fastest bullet, to the fastest spacecraft, and we are going to calculate exactly how long each one would take to cross that distance. And then, we are going to climb the ladder of propulsion technology, from the chemical rockets we use today all the way up to antimatter engines and warp drives, and we are going to see if any of them at all, can solve this problem. We are going to talk about Einstein, and why the universe has a speed limit. We are going to talk about what the space between stars actually looks like, because it is not the empty void you think it is. We are going to talk about what would happen to your body on a journey like this, and whether your mind could survive it. And finally, we are going to arrive at an answer. A real, honest, scientifically grounded answer, and it is going to be one of the most profound things you have ever heard. So if you are the kind of person who lies awake at night wondering about the size of the universe, if you are the kind of person who looks up at the stars and feels both wonder and a strange kind of loneliness, then this video was made for you. Subscribe right now, because what we do on this channel is not ordinary. We go deep. We go all the way to the bottom. And today, we are going to the bottom of one of the biggest questions humanity has ever asked. Let us begin. Let us start with something that most people think they understand, but almost nobody truly does. What is a light year? Now I know what you are thinking. You are thinking, I know what a light year is. It is the distance light travels in 1 year. And yes, technically, that is correct. But that sentence, that simple, clean textbook sentence, hides within it a scale of distance so enormous, so utterly incomprehensible, that the human brain literally cannot process it. Our brains evolved to understand distances like the length of a field, the distance to the next village, maybe the width of a continent. We did not evolve to understand distances measured in trillions of kilometers. So let me try to make you understand. Let me try to break your brain just a little, in the best possible way. Light travels at 299,792,458 meters per second. Let me say that again. In 1 single second, light covers 299,792 kilometers. That is almost 300,000 kilometers. In 1 second. To put that in perspective, the Earth's circumference is about 40,075 kilometers. That means in 1 second, light could circle the entire Earth 7.5 times in 1 second. Think about that. You blink your eyes, and in that fraction of a moment, light has already gone around the planet 7.5 times. That is how fast light moves. In 2 seconds, light has made 15 trips around the Earth. In 10 seconds, 75 trips. In 1 minute, light has circled the Earth 450 times. This is not a speed we can relate to. This is not like a fast car or a fast plane. This is something fundamentally different. This is the speed at which reality itself propagates. This is the speed at which cause and effect travel through the fabric of the universe. Now, let us extend this. Light leaves the sun and takes 8 minutes and 20 seconds to reach the Earth. That means the sunlight you see right now, the light warming your face if you step outside, left the sun over 8 minutes ago. If the sun suddenly vanished right now, poof, gone, we would not know for over 8 minutes. We would still see it shining. We would still feel its warmth. For 8 minutes and 20 seconds, we would be completely unaware that our star had disappeared. That is how vast even the distance within our own solar system is. And that is just the Earth to the Sun. That is just one astronomical unit. 1 AU. 150 million kilometers. Remember that number. 1 AU equals 150 million kilometers. Let us keep going. Light takes about 43 minutes to reach Jupiter, the giant of our solar system. It takes about 4 hours and 15 minutes to reach Neptune, the farthest major planet. And it takes about 5 hours and 28 minutes to reach Pluto, that icy dwarf planet sitting on the edge of our solar system. So even within our own solar system, light takes hours to cross from one end to the other. And our solar system, in cosmic terms, is tiny. It is a speck. It is an atom in the body of the universe. Now here is where it gets terrifying. 1 light year is the distance light travels not in a second, not in a minute, not in an hour, not in a day, but in an entire year. 365,025 days of light, screaming through the vacuum of space at 300,000 kilometers per second, without stopping, without slowing down, for an entire year. How far does it get? The answer is 9.461 trillion kilometers. Let me write that out so you can see it. 9,461,000,000 kilometers. That is 9.461 followed by 12 zeros. In miles, it is 5.879 trillion miles. In astronomical units, the Earth to Sun distance, 1 light year equals 63,241 AU. That means if you took the distance from the Earth to the Sun and laid it end to end, 63,241 times, you would finally have 1 light year. 63,241 times the Earth-Sun distance. And the nearest star is 4.25 times further than that. Let me try another way to make you feel this. Imagine you could drive a car to the stars. You get in your car, you put it in gear, and you start driving at 120 kilometers per hour, which is a typical highway speed. A comfortable cruise. How long would it take you to drive 1 light year? The answer is approximately 9 million years. 9 million years. You would need to drive without stopping, without sleeping, without eating, at highway speed for 9 million years to cover 1 light year. The entirety of recorded human history, all of our civilizations, all of our wars, all of our inventions, everything from the first cave paintings to the smartphone in your pocket, that is roughly 10,000 years. To drive 1 light year, you would need 900 times the entire length of human civilization, just driving. And remember, the nearest star is 25 light years away, so multiply that by 4. Let me try yet another comparison. A bullet from a high-powered rifle travels at about 4,000 kilometers per hour. Fast enough to kill instantly, fast enough that you cannot see it move, fast enough that it seems almost magical in its speed. If you fired a bullet toward the nearest star, how long would it take to arrive? about 270,000 years for 1 light-year. Over 1 million years for the full 4.25 light-year distance. A bullet. The fastest projectile most people will ever encounter. 1 million years. Well, how about sound? Sound travels at about 1,235 kilometers per hour in air at sea level. If somehow sound could travel through the vacuum of space, which it cannot, but if it could, it would take about 873,000 years to cross 1 light year. If you screamed right now, aimed at Proxima Centauri, your voice would arrive in approximately 3.7 million years. By then, humanity might not even exist. Now I want you to hold all of these numbers in your mind, not just as abstract figures, but as feelings. Feel the weight of 9 million years. Feel the impossible patience of a bullet traveling for 1 million years. Feel the absurdity of a scream taking nearly 4 million years to reach the nearest star. Because this is the canvas we are painting on today. This is the scale of the problem we are trying to solve. 1 light year is not just far. It is a distance so vast that it mocks every unit of measurement the human mind has ever created. Kilometers become meaningless. Miles become jokes. Even astronomical units, a measurement specifically designed for space, become unwieldy. That is why astronomers invented the light year. Not because they wanted to confuse you, but because there is literally no other way to talk about these distances without drowning in zeros. And here is something that will twist your mind even further. When you look at a star that is, say, 100 light years away, the light you are seeing left that star 100 years ago. You are not seeing the star as it is now. You are seeing the star as it was a century ago. When you look at the Andromeda Galaxy, the nearest major galaxy to the Milky Way, it is about 2.5 million light-years away. The light you see from Andromeda left that galaxy too, 5 million years ago, before Homo sapiens even existed. You are looking back in time. The night sky is not a picture of the present. It is a museum of the past. Every star you see is a ghost, a memory, a light that began its journey long before you were born and will continue long after you are gone. And the deeper you look, the further back in time you see. The James Webb Space Telescope has detected galaxies over 13.5 billion light-years away. The light from those galaxies has been traveling since nearly the beginning of the universe itself. We are seeing the cosmos as it was when it was barely a few 100 million years old. This is the profound, almost spiritual truth about light years. They are not just units of distance. They are units of time, of history, of cosmic memory. And when we ask how many years it would take humanity to cross 1 light year, we are really asking how long it would take us to close a gap that light itself takes an entire year to cross. We are asking whether our technology, our ingenuity, our species can compete with the fundamental speed of reality itself. And the answer, as we are about to discover, is humbling beyond words. But also, in a strange and beautiful way, inspiring. Now let us get to the heart of the matter. Let us talk about speed. Human speed, the speed of the machines we have built, the fastest things our species has ever created. And let us see, honestly and unflinchingly, how they measure up against the light year. Let us start with the most basic form of human movement. Walking. The average human walks at about 5 kilometers per hour. It is the speed we evolved to move at, the speed at which our ancestors crossed continents over thousands of years. If you could walk to the stars, if you could somehow put one foot in front of the other across the void of space, how long would it take to cross 1 light year? The answer is approximately 215 million years. 215 million years of walking. To put that in perspective, 215 million years ago, dinosaurs were just beginning to appear on Earth. The supercontinent Pangaea was starting to break apart. The first mammals would not appear for another 20 million years. That is the scale of time we are talking about. Walking to the stars is not just impractical. It is a concept so absurd that it borders on the surreal. But we are not a species that walks anymore. We drive, we fly, we build machines that move far faster than our legs ever could. So let us climb the speed ladder. A typical commercial aeroplane flies at about 900 kilometers per hour. At that speed, you could cross the Atlantic Ocean in about 7 hours. A comfortable routine flight. But to cross 1 light year at airplane speed, you would need about 12 million years. 12 million years of continuous flight. The entire Cenozoic era, the age of mammals, from the extinction of the dinosaurs to the present day, is about 66 million years. So at airplane speed, you could cross about 5 light years in the time it took for mammals to evolve from small, shrew-like creatures into elephants, whales and humans. 5 light years. That barely gets you past the nearest star. Let us go faster. The Concorde, that beautiful supersonic jet that used to fly passengers across the Atlantic in just 3.5 hours, travelled at about 180 kilometers per hour, more than twice the speed of sound. At Concorde speed, crossing 1 light year would take about 495,000 years, still almost 500,000 years. The Concorde was retired in 2003, and even if it were still flying, it would be laughably inadequate for interstellar travel. How about the SR-71 Blackbird, the legendary spy plane that still holds the record for the fastest air-breathing manned aircraft ever built? It could fly at 3,540 kilometers per hour, over 3 times the speed of sound, at altitudes so high the pilots could see the curvature of the Earth. At Blackbird speed, 1 light year would take about 305,000 years. Still hundreds of thousands of years. Still utterly hopeless. But these are all atmospheric vehicles. They were not designed for space. They were designed to fly within the thin shell of air that clings to our planet. Let us leave the atmosphere and enter the realm of spacecraft, where the real speeds live. The International Space Station orbits Earth at about 27,600 kilometers per hour. That is 7.66 kilometers per second. It circles the entire planet in about 90 minutes. Astronauts on the ISS watch 16 sunrises and 16 sunsets every single day. It is, by any human standard, spectacularly fast. But at ISS orbital speed, crossing 1 light year would take about 39,000 years. 39,000 years. When the last ice age was at its peak about 20,000 years ago, our ancestors were painting caves in France, and most of North America was buried under kilometers of ice. Double that time, and you have the ISS crossing 1 light year. Now let us get serious. Let us talk about the spacecraft that were actually designed to go fast, the ones built to leave Earth behind entirely and venture into deep space. Apollo 10 holds the record for the fastest speed ever achieved by a crewed vehicle. On May 26, 1969, during its return from the Moon, Apollo 10 reached a speed of 39,897 kilometers per hour. That is about 11 kilometers per second. Almost 25,000 miles per hour. The astronauts inside, Thomas Stafford, John Young and Eugene Cernan, were traveling faster than any human beings had ever traveled before. It was an extraordinary achievement, and at that speed, crossing 1 light year would take approximately 27 million years. 27 million years. Even the fastest manned vehicle in history is so pathetically slow compared to the light year that it would need longer than the entire evolution of the great apes to complete the journey. Let us move to unmanned spacecraft, the ones designed not to come back. The ones we launched into the void with the explicit intention of going as far and as fast as possible. New Horizons. Launched on January 19, 2006, New Horizons holds the record for the fastest launch speed of any spacecraft. It left Earth at 58,536 kilometers per hour, about 16.26 kilometers per second. It was moving so fast that it passed the orbit of the Moon in just 9 hours, a journey that took Apollo 10 3 days. It reached Jupiter in just over a year for a gravity assist that boosted its speed even further. And then it flew on, for 9.5 years, across the cold, dark expanse of the outer solar system until on July 14, 2015, it flew past Pluto, giving us our first close-up look at that mysterious world. It was a triumph, one of humanity's greatest achievements in space exploration. But here is the sobering truth. Pluto, at its farthest, is about 7.5 billion kilometers from Earth. That sounds like an enormous distance, and it is, by human standards. But in terms of a light year, Pluto's distance is about 0.0008 light years, less than 1,000th of a light year. New Horizons, the fastest launched spacecraft in history, took 9.5 years to travel less than 1,000th of a light year. At its launch speed, crossing one full light year would take approximately 18,400 years. 18,400 years. That is roughly the time span from the end of the last ice age to the present day. The entire history of human civilization, from the first villages in Mesopotamia to the International Space Station, fits within the time it would take New Horizons to cross one light year. And then there is Voyager 1. Oh, Voyager 1! The little spacecraft that could. Launched on September 5th, 1977, Voyager 1 is, as of today, the farthest human-made object from Earth. It is out there, right now at this very moment, flying through interstellar space at about 61,000 kilometers per hour, or roughly 17 kilometers per second. It has been traveling for nearly 49 years. And in all that time, through all those decades of silent flight through the darkness, it has covered about 172 astronomical units. That is about 25.8 billion kilometers. It sounds like a lot. And it is, in human terms. But in terms of a light year, 172 AU is approximately 0.00272 light years. Less than 3,000ths of a light year. Voyager 1, after nearly half a century of travel, has not even crossed one single light day. A light day. Not a light year. A light day. 1/365th of a light year. Voyager 1 has not even covered that much yet, even though it has been flying since before most of you watching this were born. Let that settle in. Let it really truly settle in. Humanity's most distant emissary, a spacecraft that has been flying for almost 50 years, has travelled less than one light day, and we are asking about a light year. A distance 365 times greater. At its current speed, Voyager 1 would need approximately 17,500 years to cross one light year. 17,500 years. And it would need about 73,000 years to reach the vicinity of Proxima Centauri, if it were heading in that direction, which it is not. In fact, NASA has calculated that in the year 40,272 AD, over 38,000 years from now, Voyager 1 will pass within about 7 light years of a small star in the constellation Ursa Minor. It will not reach it. It will not orbit it. It will just drift past, a silent, dead artifact of a civilization that may or may not still exist by then. Now, here is where the story gets a little bit more interesting. Because there is one spacecraft that is faster than all of these, significantly faster. It is called the Parker Solar Probe, and it is, without question, the fastest object humanity has ever built. Launched on August 12, 2018, the Parker Solar Probe was designed not to fly away from the Sun, but toward it. Its mission is to study the Sun's corona, the outermost layer of the Sun's atmosphere, by flying closer to our star than any spacecraft has ever gone before. And to do this, it uses a series of gravity assists from Venus to tighten its orbit around the Sun, getting closer and closer with each pass, and as it gets closer, it speeds up. Dramatically, on December 24, 2024, Christmas Eve, the Parker Solar Probe made its closest approach to the Sun yet, passing just 6.1 million kilometers from the Sun's surface. And during this approach, it reached a speed of approximately 692,000 kilometers per hour. 692,000 kilometers per hour. That is 192 kilometers per second. That is 430,000 miles per hour. It is by far the fastest speed any human-made object has ever achieved. At this speed, you could fly from New York to Tokyo in less than a minute. You could circle the Earth in about 3.5 minutes. You could reach the Moon in about 33 minutes. This is a speed that is difficult to even conceptualize. And yet, even at this absolutely insane speed, crossing 1 light year would take approximately 1,560 years. 1,560 years. Let me give you a sense of that timescale. 1,560 years ago, the Roman Empire had just fallen. The year was approximately 466 AD. The world was in the early Dark Ages. Islam had not yet been founded. The printing press would not be invented for another 1,000 years. The Americas were unknown to Europeans. The entire modern world, everything you know, everything you have ever experienced, fits within the time it would take the fastest thing we have ever built to cross 1 light year. And here is the truly devastating number. The Parker Solar Probe's speed of 692,000 kilometers per hour sounds enormous, and it is by human standards. But compared to the speed of light, it is 0.064% of the speed of light. 0.064%. Not even 1/10 of 1%. The fastest object humanity has ever created moves at less than 1/1500th of the speed of light. We are not just slow compared to light. We are almost stationary. We are barely moving. In the cosmic race between humanity and light, we have not even left the starting line. I want you to sit with that for a moment. I want you to really feel it. The fastest thing we have ever built, a spacecraft specifically designed to go as fast as possible. A spacecraft that literally touches the sun, that survives temperatures of over 1,300 degrees Celsius, that represents the absolute pinnacle of human engineering and technology, is moving at 0.064% of the speed of light. And at that speed, it would still need 1,560 years to cross 1 light year. The gap between our best speed and the speed of light is not a gap you can close with better engineering or more fuel. It is a chasm, an abyss, a gulf so vast that it challenges everything we thought we knew about our place in the universe. And now you might be asking yourself, but why? Why is this so hard? We have split the atom. We have decoded the human genome. We have built machines that can think. Why can we not go faster? What is stopping us? And the answer to that question takes us to one of the deepest truths in all of physics. It takes us to Albert Einstein and to a discovery he made in 1905 that changed our understanding of reality itself. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would revolutionize physics. One of those papers introduced what we now call the special theory of relativity. And within that theory lies one of the most profound and, for our purposes, one of the most frustrating truths about the universe. Nothing with mass can ever reach the speed of light. Not in theory. Not with infinite fuel. Not with infinite time. Not ever. The speed of light is not just a speed, it is a fundamental limit woven into the very fabric of space-time. It is the speed at which causality itself moves. It is the speed at which the present becomes the future. To call it the speed of light is actually a bit misleading. It would be more accurate to call it the speed of the universe, or the speed of reality. Light just happens to travel at this speed, because photons have no mass. And anything with zero mass must travel at exactly this speed. Not faster, not slower, exactly this speed. But anything with mass, anything at all, even a single electron, can never reach this speed. And the reason why is one of the most mind-bending concepts in all of science. As an object with mass accelerates and gets closer and closer to the speed of light, something strange begins to happen. The energy required to accelerate it further does not increase linearly, it increases exponentially. And as the object approaches the speed of light, the energy required approaches infinity. Let me say that again. To accelerate any object with mass to the speed of light would require an infinite amount of energy. More energy than exists in the entire observable universe. More energy than every star, every galaxy, every black hole combined could produce. Infinity, and you cannot spend infinity. You cannot generate infinity. You cannot overcome infinity. It is the universe's way of saying, this far and no further. The mathematics behind this is elegant but relentless. Einstein showed that the energy of a moving object is described by the equation E equals gamma times mc squared, where gamma, the Lorentz factor, equals 1 divided by the square root of 1 minus v squared over c squared. As v, the velocity of the object, approaches c, the speed of light, the term v squared over c squared approaches 1, which means 1 minus that approaches 0, which means the square root approaches 0, which means gamma approaches infinity. And since the energy is proportional to gamma, the energy also approaches infinity. Let me make this concrete with numbers. At 10% of the speed of light, gamma is about 1.005. The energy increase compared to classical physics is negligible, less than 1%. At this speed, the relativistic effects are barely noticeable. But at 50% of the speed of light, gamma is about 1.155. Now you need about 15% more energy than Newton's physics would predict. At 90% of the speed of light, gamma jumps to 2.29. You now need more than twice the energy that classical physics would suggest. At 99% of the speed of light, gamma is 7.09. You need 7 times the expected energy. At 99.9%, gamma is 22.37. At 99.99%, gamma is 70.71. At 99.99999%, gamma is 707. And at 99.999999%, gamma is over 70,000. The numbers explode. They rocket upward with terrifying speed as you approach the ultimate, and they never, ever reach a finite value at exactly the speed of light. The wall is absolute. This is not just a mathematical curiosity. This is a physical reality that has been confirmed by every experiment ever conducted. Particle accelerators like the Large Hadron Collider at CERN routinely accelerate protons to 99.9999991% of the speed of light. And to achieve this, they use superconducting magnets that consume enormous amounts of energy. And the protons are subatomic particles with a mass of just 1.67 times 10 to the negative 27 kilograms. Essentially nothing. And yet, even for something that small, reaching near light speed requires immense energy. Now imagine trying to do the same thing with a spacecraft weighing tens of thousands of kilograms. The numbers become not just impractical but genuinely, physically impossible with any conceivable technology. Let us put some numbers to this. To accelerate a 1 kilogram object, just 1 kilogram, to 10% of the speed of light, you would need approximately 450 trillion joules of energy. That is 4.5 times 10 to the 14th power joules. To give you a sense of scale, the atomic bomb that destroyed Hiroshima released approximately 63 trillion joules. So to push 1 kilogram to 10% light speed, you would need the energy of roughly 7 Hiroshima bombs. For 1 kilogram. Now imagine a spacecraft. Even a modest unmanned probe might weigh 1,000 kilograms. To push it to 10% light speed, you need 7,000 Hiroshima bombs worth of energy. A crewed spacecraft? 100,000 kilograms? That is 700,000 Hiroshima bombs. Just to reach 10% of light speed. And 10% of light speed, while fast enough to cross a light year in about 10 years, is still far below what we would ideally want for interstellar travel. To reach 50% of the speed of light, the energy requirements become staggering. For a 100,000 kilogram spacecraft, you would need energy equivalent to millions of nuclear weapons. The total annual energy production of the entire human civilization is about 580 exajoules, or 5.8 times 10 to the 20th joules. To accelerate a large spacecraft to 50% light speed would require a significant fraction of that annual output, or even multiple years' worth, depending on the mass. And that is just the acceleration. You also need to decelerate at the other end, which requires just as much energy. So double it. The energy problem is not just an engineering challenge. It is a civilizational challenge. It requires energy on a scale that our entire species has never produced, concentrated into a single propulsion system. But there is a silver lining to Einstein's universe. Because while special relativity tells us we can never reach the speed of light, it also gives us something extraordinary in return. Something that might, in a strange and beautiful way, help us with the light-year problem. It is called time dilation, and it is one of the most counterintuitive and mind-warping phenomena in all of physics. Time dilation is this: the faster you move, the slower time passes for you relative to someone who is standing still. This is not a metaphor. This is not an illusion. This is a literal, physical, measurable effect. Clocks that are moving relative to an observer tick more slowly, and the closer you get to the speed of light, the more pronounced the effect becomes. At everyday speeds, the effect is negligible. If you drive your car at 100 kilometers per hour for a year, time dilation will cause your clock to fall behind a stationary clock by about a few nanoseconds. Completely undetectable without atomic clocks, but at significant fractions of light speed, the effect becomes dramatic. At 50% of the speed of light, time passes about 15% more slowly for the traveler. So if you traveled at half the speed of light for what you experienced as 1 year, about 1.5 fine years would have passed on Earth. A noticeable difference, but not a dramatic one. At 90% of the speed of light, things get interesting. Time passes 2.29 times more slowly for the traveler. So 1 year of your time equals 2.29 years on Earth. You would cross 1 light year in about 1 year and 1 month of your personal time, while about 2.5 years pass on Earth. At 99% of the speed of light, time dilation becomes severe. 1 year of your time equals 7.09 years on Earth. You could cross 1 light year in about 2 months of your own experience. At 99%, 1 year of your time equals 22.37 years on Earth. 1 light year passes in about 16 days of your subjective time. At 99.99%, 1 year equals 70.71 Earth years. You cross a light year in about 5 days, and at 99.9999% of the speed of light, the gamma factor is 707. You could theoretically cross an entire light year in about 12 hours of your own experience. Half a day, but 707 days would pass on Earth, almost 2 years. This is remarkable. It means that from the traveler's perspective, the universe can be crossed in a human lifetime as long as you can get close enough to the speed of light. The problem, as we have just discussed, is getting there. The energy requirements are prohibitive. But the physics allows it. If you could somehow reach 99% of light speed, the entire Milky Way galaxy, 100,000 light years across, could theoretically be traversed in about 140 years of ship time, the galaxy in a lifetime. But 100,000 years would pass on Earth. Everyone you ever knew would be dust. Your civilization might not even exist anymore. This is the twin paradox, and it is one of the most emotionally devastating thought experiments in all of physics. Imagine you are an astronaut. You leave Earth on an interstellar voyage at 99.99% of the speed of light. You travel for what feels to you like 1 year. You explore. You discover. And then you turn around and come home. For you, 2 years have passed, but when you arrive back at Earth, you discover that 141 years have gone by. Everyone you loved is dead. The world has changed beyond recognition. Languages have shifted. Nations have risen and fallen. Technology has advanced in ways you cannot understand. You are a stranger in your own world, a relic, a time traveler, but only in one direction. This is the cruel gift of relativity. It lets you cheat time, but it takes everything you love in exchange. The faster you go, the more the universe ages around you. The speed of light is not just a speed limit, it is a wall between you and everyone you leave behind. But let us not despair. Let us instead ask the most important question of all. Is there any way we can actually do this? Is there any propulsion technology, either existing or theoretical, that could allow humanity to cross 1 light year in a reasonable time? Let us climb the technology ladder from the bottom rung to the very top and find out. The bottom rung is where we are right now. Chemical rockets. The workhorses of the space age. Every rocket that has ever left Earth's surface has used some form of chemical propulsion. The Space Shuttle, the Saturn V, the Falcon 9, the Ariane 5, all of them burn fuel, either solid or liquid, and expel the exhaust at high speed to generate thrust. This is Newton's third law in its most literal form. For every action, there is an equal and opposite reaction. Push hot gas out the back, and the rocket moves forward. Chemical rockets work. They have carried humans to the moon, probes to every planet, and telescopes into orbit. But for interstellar travel, they are utterly, hopelessly inadequate. And the reason why comes down to something called the Tsiolkovsky rocket equation, named after the Russian scientist Konstantin Tsiolkovsky, who first derived it in 1903, the same year the Wright brothers flew. The rocket equation describes the fundamental relationship between a rocket's speed, the speed of its exhaust, and the ratio of its total mass to its empty mass. And it contains a devastating truth. The relationship is exponential. To double your final speed, you do not need to double your fuel, you need to square it. To triple your speed, you need to cube it. The amount of fuel required to reach a given speed grows exponentially, which means that for very high speeds, the amount of fuel required quickly becomes absurd. For chemical rockets, the exhaust velocity is typically between 2.5 and 4.5 kilometers per second. The best chemical rockets, burning liquid hydrogen and liquid oxygen, achieve an exhaust velocity of about 4.4 kilometers per second. To reach even 1% of the speed of light, which is about 3,000 kilometers per second, using chemical propulsion, you would need a fuel-to-payload ratio so enormous that no conceivable spacecraft could carry it. The numbers work out to something like 10 to the power of 300 kilograms of fuel for every kilogram of payload. That is a number so large it has no physical meaning. There are only about 10 to the 80th atoms in the entire observable universe. You would need more fuel than there are atoms in the cosmos. Chemical rockets cannot reach even 1% of light speed. Period. End of discussion. For interstellar travel, they are a dead end. And that is why, even though we have been launching rockets for over 80 years, even though we have reached every planet in our solar system, we have never come close to interstellar speeds. The fundamental technology we use, chemical propulsion, is simply incapable of it. It is like trying to cross the Pacific Ocean in a bathtub. No matter how good you are at rowing, the bathtub is the wrong vehicle. So let us climb to the next rung, ion propulsion, also known as electric propulsion. This is a technology that has been used in space, and it represents a genuine step forward. Ion engines work by ionizing a propellant, usually xenon gas, and then accelerating those ions using electric fields. The ions are ejected at very high speeds, typically 20 to 50 kilometers per second, which is 5 to 10 times faster than the exhaust from a chemical rocket. This means ion engines are fundamentally more efficient at converting fuel into speed. But there is a catch. The big one. The thrust produced by an ion engine is incredibly small. We are talking about forces measured in fractions of a Newton. To give you an analogy, the thrust of a typical ion engine is about the same as the weight of a sheet of paper resting on your hand. You can barely feel it. But here is the beauty of ion propulsion: it does not need to be powerful. It needs to be patient. An ion engine can fire continuously for months or even years. slowly, steadily accelerating the spacecraft to higher and higher speeds. It is the tortoise to the chemical rocket's hare. Low thrust, but sustained over incredibly long periods. NASA's Deep Space One mission was one of the first to use ion propulsion in deep space, and it proved the concept worked. The Dawn mission used ion engines to orbit two different bodies in the asteroid belt, Vesta and Ceres, something that would have been impossible with chemical rockets due to the fuel requirements. And SpaceX's Starlink satellites use ion thrusters for orbit maintenance. The theoretical maximum speed achievable with ion propulsion depends on how long you can fire the engine and how much propellant you carry, but estimates suggest somewhere around 100 to 200 kilometers per second might be achievable with advanced ion drives and sufficient power. At 100 kilometers per second, crossing 1 light year would take about 3,000 years. At 200 kilometers per second, about 5,500 years. Better than chemical rockets by an order of magnitude, but still thousands of years. And ion engines require electricity to power them, which means either solar panels, which become useless beyond a few AU from the sun, or nuclear reactors, which adds mass and complexity. Ion propulsion is a step in the right direction, but it is still a baby step on the scale of interstellar distances. The next rung up the ladder takes us into the realm of nuclear power, and this is where things start to get genuinely exciting. Because nuclear reactions, whether fission or fusion, release millions to hundreds of millions of times more energy per kilogram than chemical reactions. If we can harness this energy for propulsion, we can theoretically reach speeds that are orders of magnitude faster than anything chemical rockets can achieve. The first serious concept for nuclear propulsion was nuclear thermal propulsion, or NTP. The idea is straightforward: use a nuclear fission reactor to heat a propellant, typically liquid hydrogen, to extremely high temperatures, and then expel it through a nozzle. Because the reactor can heat the hydrogen to much higher temperatures than chemical combustion, the exhaust velocity is about twice that of the best chemical rockets, around 8 to 9 kilometers per second. This translates to a specific impulse of about 900 seconds, compared to about 450 seconds for liquid hydrogen and liquid oxygen. NASA actually built and tested nuclear thermal engines in the 1960s and 70s under the NERVA program, which stands for Nuclear Engine for Rocket Vehicle Application. These engines worked, they were ground tested, and they performed as predicted. NERVA was originally intended to power crewed missions to Mars, and it could have cut the travel time to Mars from 7 or 8 months to as little as 3 or 4 months. But the program was cancelled in 1973 due to budget cuts and shifting political priorities. One of the great tragedies of the space age. We had a working nuclear rocket engine 50 years ago, and we shelved it. Recently, there has been a revival of interest in nuclear thermal propulsion. NASA and DARPA have launched the Draco program, which aims to demonstrate a nuclear thermal rocket engine in space. This could eventually enable faster trips to Mars and beyond. But even with nuclear thermal propulsion, the speeds achievable are still limited, maybe 20 to 50 kilometers per second. Crossing 1 light year would take somewhere between 6,000 and 14,000 years. Better than chemical rockets, but still firmly in the realm of multi-millennium voyages. But what if we used nuclear energy in a much more dramatic, much more extreme way? What if, instead of using a nuclear reactor to heat propellant, we simply detonated nuclear bombs behind our spacecraft and rode the shockwave? This sounds insane. It sounds like something out of a science fiction movie. But it was a real, funded, serious engineering project. And it might be the most audacious thing humanity has ever conceived. It was called Project Orion, and it ran from 1958 to 1965, funded by DARPA and the United States Air Force. The concept was breathtaking in its simplicity and terrifying in its audacity. You build a large spacecraft with a massive, thick steel plate at the back, called a pusher plate. Behind the pusher plate, you eject small nuclear bombs, one at a time. Each bomb detonates, and the force of the explosion hits the pusher plate, pushing the spacecraft forward. Giant shock absorbers between the pusher plate and the rest of the ship smooth out the ride. Then you eject another bomb, and another, and another. Hundreds, thousands, tens of thousands of nuclear detonations, each one giving the ship a powerful kick. The physics of Project Orion are absolutely sound. The calculations showed that an Orion-type spacecraft could achieve exhaust velocities of hundreds of kilometers per second. The larger designs, ships hundreds of meters across carrying thousands of nuclear charges, could theoretically reach 3 to 5% of the speed of light. 5% of the speed of light is 15,000 kilometers per second. At that speed, crossing 1 light year would take about 20 years. 20 years. Not thousands, not millions. 20. A single human lifetime. And the technology to build it existed in the 1960s. We had nuclear bombs. We had steel. We had shock absorbers. The engineering challenges were significant but not insurmountable. Freeman Dyson, one of the greatest physicists of the 20th century, worked on the project and was convinced it could work. He later said that Project Orion was the most exciting thing he had ever worked on, and its cancellation was one of his greatest regrets. So why did it die? The answer is politics, not physics. In 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Nuclear Test Ban Treaty, which prohibited nuclear explosions in space, in the atmosphere, and underwater. Project Orion, which relied on detonating nuclear weapons in space, was suddenly illegal. The project was cancelled, and with it, humanity's most realistic near-term path to interstellar travel was shelved. Think about that. In the 1960s, we had a viable plan to build a spacecraft that could cross 1 light year in 20 years. And we chose not to build it. The political and environmental concerns were legitimate. The idea of detonating thousands of nuclear weapons is genuinely horrifying. But the fact remains, the technology was there. The physics worked. And we walked away. Later projects built on the Orion concept pushed even further. Project Daedalus, a study by the British Interplanetary Society in the 1970s, designed a spacecraft that would use nuclear fusion rather than fission, specifically the fusion of deuterium and helium-3. Daedalus was designed to reach Barnard's star, 5,009 light-years away, in about 50 years. Its cruise speed would be approximately 12% of the speed of light. At 12% light speed, crossing 1 light year would take about 8.3 years. 8 years, less than a decade, within a single human career. But Daedalus had its own problems. The fuel, helium-3, is extremely rare on Earth. The design called for mining it from the atmosphere of Jupiter, which is, to put it mildly, a significant logistical challenge. The ship itself would be enormous, about 54,000 tons, most of which would be fuel. And it was a flyby mission only, no deceleration. The spacecraft would scream past Barnard's star at 12% of light speed, getting a brief window to collect data before vanishing into the interstellar void. Project Icarus, a modern successor to Daedalus, has been working on updated designs that address some of these limitations. The goal is a fusion-powered starship that could not only reach a nearby star within a human lifetime, but also decelerate and enter orbit. The challenges are immense, but the fundamental physics is sound. And this brings us to the critical bottleneck. Fusion. Nuclear fusion is the process that powers the sun. It works by fusing light elements, typically isotopes of hydrogen, into heavier elements, releasing enormous amounts of energy in the process. Gram for gram, fusion releases about 4 million times more energy than chemical combustion. If we could harness fusion for propulsion, we could achieve exhaust velocities of thousands of kilometers per second, enabling spacecraft speeds of 10 to 15% of light speed, or potentially more. But here is the problem. As of now, we have not achieved sustained, controlled fusion on Earth for power generation. We have fusion weapons, hydrogen bombs, which demonstrate that fusion works, and we have experimental reactors like ITER in France, and various private fusion companies that are making progress. but practical fusion power has been 30 years away for the past 60 years. The engineering challenges are formidable, containing plasma at temperatures of hundreds of millions of degrees, maintaining the conditions for fusion to occur, extracting more energy than you put in. These are not trivial problems, but there is reason for optimism. Multiple private companies are pursuing novel approaches to fusion, and several have achieved significant milestones. If and when we crack fusion, not just for power generation but for propulsion, interstellar travel shifts from a pipe dream to an engineering project, a massive, expensive, multi-generational engineering project, but an engineering project nonetheless. Fusion propulsion could give us the ability to cross 1 light year in under a decade. And that changes everything. Now let us go higher. Let us climb to a rung on the technology ladder that makes even nuclear fusion look quaint. Let us talk about antimatter. Antimatter is the mirror image of normal matter. For every particle of matter, there exists a corresponding antiparticle with the same mass but opposite charge. The electron has the positron, the proton has the antiproton, the neutron has the antineutron. And when a particle meets its antiparticle, something extraordinary happens. They annihilate, both particles are destroyed, and their entire mass is converted into pure energy, usually in the form of gamma rays. This is E equals mc squared in its most literal, most violent form. 100% of the mass becomes energy. Compare this to other energy sources. Chemical combustion converts about 0.00001% of mass to energy. Nuclear fission converts about 0.1%. Nuclear fusion converts about 0.7%. Antimatter converts 100%. It is the most energy-dense fuel source that the laws of physics allow. The numbers are staggering. 1 gram of antimatter combined with 1 gram of normal matter would release approximately 180 trillion joules of energy. That is equivalent to about 43 kilotons of TNT, roughly 3 times the energy of the Hiroshima bomb, from 2 grams of material. Just 1 kilogram of antimatter could theoretically produce enough energy to accelerate a spacecraft to a significant fraction of the speed of light. Some calculations suggest that an antimatter-powered spacecraft could reach 40 to 70% of light speed, potentially even higher with optimized designs. At 50% of light speed, crossing 1 light year would take just 2 years. 2 years. The same time it takes to get a master's degree. The same time between 2 World Cups. 2 years across a distance that would take Voyager 17,500 years. But, and this is a very, very big but, antimatter is almost impossibly difficult to produce, store, and use. Here is why. First, production. We can make antimatter. Particle accelerators like CERNs produce antiparticles routinely. But they produce them in vanishingly small quantities. The total amount of antimatter produced by all of humanity's particle accelerators throughout all of history is estimated at roughly 20 nanograms. 20 billionths of a gram. To fuel an interstellar spacecraft, we would need kilograms. At current production rates, it would take millions of years to produce enough antimatter for a single interstellar voyage. Second, cost. Because of the enormous energy required to produce antimatter, it is the most expensive substance in the universe. Estimates put the cost at approximately $62.5 trillion per gram. The entire global GDP is about $100 trillion. So 1 gram of antimatter costs about 2/3 of the entire world's economic output for a year. 1 kilogram would cost more than all the money that has ever existed in human history. Third, storage. Antimatter annihilates on contact with any normal matter. Any normal matter at all. Air, metal, glass, your hand, anything. To store antimatter, you need to suspend it in a perfect vacuum using magnetic fields that prevent it from touching the walls of its container. These are called penning traps, and they work for tiny quantities, but scaling up to grams, let alone kilograms, of antimatter storage is an engineering challenge of almost inconceivable difficulty. One failure, one tiny breach in the magnetic containment, and you get an explosion equivalent to a nuclear bomb. So antimatter propulsion is the ultimate tease. The physics is perfect, the energy density is unmatched, the speeds achievable are exactly what we need, but the practicalities are so far beyond our current capabilities that it might as well be magic. For now. But technology has a way of making the impossible routine. 50 years ago, the idea of carrying a computer in your pocket would have seemed like science fiction. Who knows what we will be able to do in 200 or 500 years? Let us now turn to a propulsion concept that is very different from everything we have discussed so far. One that does not require the spacecraft to carry any fuel at all. It is called the laser sail, or light sail, and it is the basis of one of the most ambitious and exciting projects in interstellar travel, Breakthrough Starshot. The concept is elegantly simple. You build a tiny spacecraft, really tiny, maybe just a few grams, with a large, thin, highly reflective sail. You position a massive array of lasers on Earth or in Earth orbit, and then you fire the lasers at the sail. The photons from the lasers bounce off the sail, transferring their momentum to the spacecraft. The push from each photon is tiny, but with a powerful enough laser array, the cumulative force can accelerate the tiny spacecraft to extraordinary speeds. Breakthrough Starshot, announced in 2016 with funding from Russian-Israeli billionaire Yuri Milner and with the late Stephen Hawking as one of its board members, aims to send gram-scale probes to Alpha Centauri at 20% of the speed of light. 20%. That is 60,000 kilometers per second. At that speed, the probes would reach Alpha Centauri in about 20 to 25 years, and they would cross 1 light year in approximately 5 years. 5 years to cross a light year. That is within a human attention span. That is a timescale we can actually relate to. It is roughly the same as a term of a government, the same as going from starting a degree to finishing a graduate program. 5 years. Not thousands, not millions. 5. But there are challenges. Enormous challenges. The laser array would need to produce on the order of 100 gigawatts of power. That is more than the entire electrical generation capacity of most countries on Earth. Keeping the laser beam focused and aimed at a sail that is millions of kilometers away and moving at a significant fraction of the speed of light is an engineering problem of the highest order. The probes themselves are incredibly small, just a few grams, which means they can carry only the most basic instruments: a camera, a communication system, maybe a simple spectrometer. No humans. No complex scientific instruments. Just a tiny chip with a sail, hurtling through the void at 1/5 the speed of light. And perhaps the biggest challenge of all, deceleration. The laser can push the sail, but it cannot pull it. Once the probes reach Alpha Centauri, they will be moving at 20% of light speed with no way to slow down. They will scream past the star system in a matter of hours, getting a brief window to take pictures and collect data before vanishing into the interstellar void. A flyby, not a visit. A glimpse, not an exploration. Despite these challenges, Breakthrough Starshot represents the most realistic near-term pathway to interstellar travel. Not for humans, not yet, but for our machines. Our tiny, brilliant, incredibly fast machines. And if we can do it for a gram-scale probe, perhaps in time we can scale it up. Perhaps decades or centuries from now, we can build laser arrays powerful enough to push larger spacecraft, carrying more instruments, and eventually, one day, carrying people. There is one more propulsion concept I want to discuss before we move on. It is one of the most beautiful and romantic ideas in all of interstellar travel, even though it probably does not work. It is called the Bussard ramjet, and it was proposed by physicist Robert Bussard in 1960. The concept is poetry in motion. As you fly through interstellar space, you scoop up the hydrogen atoms that are scattered thinly throughout the interstellar medium. You funnel these atoms into a fusion reactor at the heart of your ship, fuse them, and use the energy to accelerate. The faster you go, the more hydrogen you scoop up and the more thrust you produce. It is a self-feeding engine, a spacecraft that fuels itself from the very fabric of space. The beauty of the Bussard ramjet is that it solves the fuel problem entirely. You do not need to carry your fuel with you. The universe provides it. In principle, a Bussard ramjet could accelerate continuously, getting faster and faster, potentially approaching the speed of light over long periods. At near light speeds, it could cross a light year in just over a year from the perspective of an outside observer, and much less from the perspective of the crew, thanks to time dilation. But the dream has been shattered by detailed calculations. The interstellar medium is incredibly sparse, about 1 hydrogen atom per cubic centimetre on average. To scoop up enough hydrogen to fuel a fusion reactor, you would need an electromagnetic scoop hundreds or thousands of kilometres across. The energy required to maintain such a magnetic field is enormous, and worse, the drag created by the scoop interacting with the interstellar medium may actually exceed the thrust produced by the engine. In other words, the Bussard ramjet might not be an engine at all. It might be a brake. The faster you go, the more drag you experience, and the harder it becomes to accelerate. Recent calculations have confirmed this grim assessment, and most physicists now consider the Bussard ramjet to be physically impractical, if not outright impossible. It is a beautiful idea that does not survive contact with reality. But science is full of beautiful ideas that did not work, and each one teaches us something valuable about the limits and possibilities of the universe. So let us now take a step back and survey the landscape we have just crossed. We have climbed the entire propulsion technology ladder, from chemical rockets at the bottom to antimatter and laser sails near the top. And what have we found? With chemical rockets, crossing 1 light year takes 18 to 30,000 years or more. With ion drives, about 3,000 years. With nuclear thermal propulsion, 6,000 to 14,000 years. With nuclear pulse propulsion like Project Orion, about 20 years. With fusion propulsion like Project Daedalus, about 8 years. With antimatter, about 2 years. With laser sails like Breakthrough Starshot, about 5 years. And with hypothetical technologies like the Bussard ramjet, perhaps 1 to 2 years if they worked, which they probably don't. The pattern is clear. With our current technology, crossing 1 light year is a journey of millennia. With technology we could plausibly build within the next century, it drops to decades. And with technology that is theoretically possible but far beyond our current capabilities, it drops to just a few years. The light year is not an absolute barrier. It is a technology barrier. And technology barriers throughout human history have a way of falling. But wait, we have been talking as if speed is the only problem. It is not. Even if we could build a spacecraft fast enough to cross a light year in a reasonable time, we would still face a host of other challenges that are just as formidable, if not more so. Because the space between the stars is not the empty, peaceful void that most people imagine. It is a dangerous, hostile, unforgiving wilderness. And any spacecraft crossing it would need to survive not just the speed, but the journey. Let me take you on a tour of interstellar space. Not the glamorous, star-studded vision from science fiction. The real thing. The space between stars is called the interstellar medium, and the first thing you need to know about it is that it is not empty. It is very, very thin, far thinner than the best vacuum we can create on Earth. But it is not nothing. The interstellar medium contains gas, mostly hydrogen and helium, at a density of roughly 1 atom per cubic centimetre. It contains dust, microscopic grains of silicates and carbon compounds, scattered incredibly sparsely but present. It contains cosmic rays, high-energy particles travelling at near light speeds, remnants of supernova explosions and other violent cosmic events. It contains magnetic fields, weak but pervasive. And occasionally, it contains surprises, rogue planets, brown dwarfs, comets, asteroids, and other objects drifting through the void, untethered to any star. Our solar system sits within a region of the interstellar medium called the local bubble, a roughly 1,000 light-year wide cavity of unusually low-density gas. This bubble was carved out by a series of supernova explosions that occurred millions of years ago, sweeping the gas outward and leaving behind a region of hot, thin gas. It is a relatively benign neighborhood, as interstellar neighborhoods go, but even within this bubble, a spacecraft traveling at high speed would face significant dangers. Let us start with dust. At everyday speeds, a microscopic dust grain is completely harmless. You could hold one on the tip of your finger and not even feel it, but at relativistic speeds, a dust grain becomes a weapon of devastating power. The kinetic energy of a moving object is proportional to the square of its velocity. Double the speed and you quadruple the energy. Increase the speed by a factor of 1,000 and you increase the energy by a factor of 1,000,000. At 10% of the speed of light, which is 30,000 kilometers per second, a dust grain weighing just 1 milligram carries kinetic energy equivalent to several hand grenades. A grain of sand, maybe 1/10 of a gram, would hit with the force of a small bomb. And at 50% of the speed of light, even a single hydrogen atom impacts with enough energy to cause measurable damage. A study published in the Journal of Space Safety Research examined the dangers of high-speed interstellar travel and concluded that at velocities above 10% of the speed of light, the interstellar medium becomes genuinely lethal. Hitting even a small pebble at half the speed of light would release energy comparable to a nuclear explosion. The spacecraft would need to be armored against constant bombardment by particles ranging from atoms to small rocks. And the shielding would need to withstand impacts of extraordinary violence. Several shielding concepts have been proposed. Whipple shields, named after the astronomer Fred Whipple, use multiple thin layers of material separated by gaps. When a microparticle hits the first layer, it vaporizes, and the resulting cloud of debris is spread over a larger area before hitting the next layer. Each successive layer absorbs more of the energy. This technique is already used on the International Space Station to protect against micrometeorites, but it would need to be vastly scaled up for an interstellar voyage at relativistic speeds. Electromagnetic shields have also been proposed. A powerful magnetic field generated around the spacecraft could deflect charged particles, much like the Earth's magnetosphere deflects the solar wind. But this would not protect against neutral particles, and maintaining a magnetic field strong enough to deflect particles moving at relativistic speeds would require enormous energy. Another option is a physical shield, a massive slab of material at the front of the spacecraft that absorbs impacts. This has the advantage of simplicity, but the disadvantage of mass. A shield thick enough to protect against decades of impacts at high speed would be enormously heavy, adding to the propulsion requirements. In reality, any interstellar spacecraft would probably use a combination of all these approaches: electromagnetic deflection for charged particles, multiple Whipple shield layers for small debris, and a robust physical shield for larger objects. And even then there would be some irreducible risk. A sufficiently large object, an asteroid or rogue planet lying undetected in the spacecraft's path, would be catastrophic regardless of shielding. But dust and debris are not the only dangers. Cosmic radiation is another, and in many ways it is more insidious. Galactic cosmic rays are high-energy particles, mostly protons and atomic nuclei, that permeate all of interstellar space. They originate from supernova remnants, active galactic nuclei, and other energetic sources. Their energies range from millions to trillions of electron volts, and the most energetic cosmic rays carry as much kinetic energy as a fast-pitched baseball, concentrated in a single subatomic particle. On Earth, we are protected from cosmic rays by two shields: the Earth's magnetic field, which deflects charged particles, and the atmosphere, which absorbs them. Astronauts on the International Space Station receive about 150 millisieverts of radiation per year, roughly equivalent to 150 chest X-rays. This is manageable for missions of a year or two, but it increases the long-term risk of cancer and other health effects. In interstellar space, there is no magnetic field to protect you, and no atmosphere to absorb the radiation. The radiation exposure would be significantly higher, perhaps several hundred millisieverts per year or more, depending on the specific environment. Over a multi-year or multi-decade journey, the cumulative dose could be life-threatening. Chronic radiation exposure causes DNA damage, increasing the risk of cancer. It damages the central nervous system, potentially leading to cognitive decline. It weakens the cardiovascular system. It can cause cataracts. And it damages electronics, causing bit flips in computer memory, degradation of sensors, and gradual failure of communication systems. Shielding against cosmic rays is technically possible but difficult. Water is one of the most effective shields, and some designs for interstellar spacecraft include thick water walls surrounding the habitable areas. Hydrogen-rich materials like polyethylene are also effective. Some designs propose using the spacecraft's own fuel as a radiation shield during the journey. And electromagnetic shielding, creating an artificial magnetosphere around the ship, is another option, though it requires significant energy. For an unmanned probe traveling at high speed for a few years, cosmic radiation is manageable. For a crewed mission lasting decades or longer, it is a serious concern that must be addressed in the ship's design from the very beginning. And then there is the cold. Interstellar space is cold. Very cold. The temperature of the interstellar medium is about 2.7 Kelvin, just 2.7 degrees above absolute zero. This is the temperature of the cosmic microwave background, the remnant radiation from the Big Bang that permeates all of space. At this temperature, any exposed surface will radiate away its heat rapidly, and the spacecraft's thermal management systems will need to work continuously to maintain habitable temperatures inside. But the cold is also an opportunity. Many electronic systems and sensors work better at low temperatures. Superconducting magnets, which could be used for both shielding and propulsion, require extremely cold temperatures to function, and cryogenic storage of fuel becomes easier when the ambient temperature is already near absolute zero. Perhaps the most psychologically challenging aspect of interstellar travel is the darkness. Beyond the outer reaches of our solar system, there is no sunlight. Not dim sunlight. Not distant sunlight. No sunlight. The sun, which has been the companion of every human being who has ever lived, which has warmed our faces and marked our days and governed our seasons since before our species existed, the sun becomes just another star. A bright dot in the sky, growing dimmer with each passing year until it is indistinguishable from the millions of other stars in the firmament. There is no dawn. There is no sunset. There is no weather. There is no horizon. There is nothing but the ship, the stars, and the vast, silent, utterly empty ocean of space. For a few years this might be tolerable, exotic even, but for decades? For centuries? For generations? The psychological impact would be profound. Humans are creatures of the earth. We evolved under an open sky, with the warmth of the sun on our skin, with the sound of wind and water, with the feel of soil beneath our feet. To cut all of that away, to seal a community of humans inside a metal cylinder flying through an infinite void for years or decades or centuries on end, is a psychological experiment that has never been attempted and whose outcome is genuinely unknown. Mars simulation experiments like Mars 500 and High Seas have given us some insight. In these experiments, small crews of volunteers were isolated in habitat modules for periods of up to 520 days, simulating the conditions of a Mars mission. The results were concerning. Participants experienced depression, interpersonal conflicts, sleep disturbances, cognitive fatigue, and motivational decline, and these experiments lasted less than 2 years, with the participants knowing that the outside world was right there, just beyond the habitat walls. An interstellar crew would face isolation measured in years or decades, with no possibility of rescue and no connection to anyone outside the ship, except through radio signals delayed by years. This brings us to one of the most important and often overlooked questions in interstellar travel. What happens to the humans? We have been talking about speeds and propulsion systems and travel times, but we have been treating the journey as if it were just a matter of getting from point A to point B. In reality, any crewed interstellar mission must solve a problem that is at least as challenging as the propulsion problem, keeping the humans alive, healthy, and sane for the duration of the voyage. The effects of spaceflight on the human body are well documented from decades of experience on the International Space Station and, before that, on the Russian Mir station. And the picture is not encouraging. In microgravity, the human body begins to deteriorate almost immediately. Without the constant pull of gravity, bones lose mineral density at a rate of about 1 to 2% per month. Muscles atrophy, losing up to 20% of their mass in just 2 weeks without countermeasures like exercise. The heart, which on Earth must pump blood against the pull of gravity, begins to weaken and shrink. Fluids in the body which on Earth are pulled down into the legs redistribute toward the head, causing facial puffiness, increased intracranial pressure, and a constellation of vision problems known as spaceflight-associated neuroocular syndrome, or SANS. The immune system becomes dysregulated, with some components becoming overactive and others suppressed. And DINA accumulates damage from cosmic radiation, increasing the long-term risk of cancer. NASA astronaut Scott Kelly spent 340 consecutive days on the International Space Station, and when he returned to Earth, scientists found measurable changes in his gene expression, his gut microbiome, his cognitive function, and even the length of his telomeres, the protective caps on the ends of chromosomes. Cosmonaut Valery Polyakov holds the record for the longest single spaceflight, spending 437 days aboard the Mir station. He experienced many of the same effects. Both men recovered after returning to Earth's gravity, but the question remains, what would happen after years? After decades? After a lifetime? For a multi-year or multi-decade interstellar voyage, the effects of microgravity would be catastrophic if not addressed. And the most promising solution is one that science fiction has depicted for decades: artificial gravity through rotation. If you spin a section of the spacecraft or the entire spacecraft, the centrifugal force created by the rotation can simulate gravity. The faster the spin and the larger the radius, the closer the simulated gravity approaches to Earth's gravity. But there are constraints. If the radius is too small, the Coriolis effect, a force created by the rotation that acts on moving objects inside the spinning section, becomes uncomfortably strong. At small radii, you would feel noticeably different gravity at your head versus your feet. You would experience dizziness when turning your head. Walking would feel strange. These effects are minimized by using a larger radius, typically at least 200 to 500 meters. This means a spinning section that is 400 to 1,000 meters in diameter, much larger than any spacecraft ever built. But for an interstellar voyage, this scale is not unreasonable. The ship would need to be large enough to sustain a community for years or decades anyway. If artificial gravity is implemented, most of the physiological effects of microgravity can be mitigated. Bones maintain their density. Muscles maintain their strength. The cardiovascular system functions normally. Fluid distribution normalizes. It is not a perfect solution. We do not yet know whether the Coriolis effect and other rotational artifacts have long-term health consequences, but it is far better than pure microgravity. But even with artificial gravity, the psychological challenges remain. And for journeys that last longer than a single human lifetime, the challenges multiply. This brings us to three of the most fascinating concepts in all of interstellar travel: cryogenic sleep, generation ships, and the uploading of consciousness. Each is a different answer to the same fundamental question: how do you keep humans alive and functional across the enormous timescales of interstellar travel? Cryogenic sleep, or more accurately cryonic suspension, is the idea of cooling the human body to extremely low temperatures, essentially putting it into a state of suspended animation for the duration of the voyage. The passengers would be frozen at the beginning of the journey and thawed at the end, experiencing no subjective time during the transit. From their perspective, they would close their eyes on one world and open them on another. The concept is compelling, but the reality is daunting. The fundamental problem is ice. When cells freeze, the water inside them forms ice crystals. These crystals are sharp, and they puncture cell membranes, destroying the cell. This is why frostbite kills tissue. To freeze a human being and thaw them later without fatal cell damage is, with current technology, impossible. There is a technique called vitrification that offers a potential solution. Instead of allowing ice crystals to form, vitrification uses cryoprotectant chemicals to convert the water in cells into a glass-like amorphous solid, bypassing the crystalline phase entirely. This technique has been used successfully to preserve small biological samples, embryos, and even small organs, but scaling it up to an entire human body is an enormously complex challenge. Every cell in the body needs to be perfused with a cryoprotectant before cooling, and the cooling needs to be uniform enough to prevent thermal stresses that could crack tissues. No one has successfully vitrified and revived a human organ, let alone a whole body. A more near-term approach is torpor, a state of reduced metabolic activity similar to hibernation in animals. Research has shown that by cooling the body to about 10 degrees Celsius, metabolism can be reduced by up to 90%. Therapeutic hypothermia, where the body is cooled to around 32 to 34 degrees Celsius, is already used in hospitals to protect the brain during certain surgeries and after cardiac arrest. Extending this to deeper cooling for longer periods is an active area of research. If perfected, torpor could allow astronauts to sleep through multi-year journeys, dramatically reducing the food, water, and psychological resources needed. But even torpor is not without risks, and maintaining a human body in a state of reduced metabolism for years or decades is territory we have not yet explored. If cryogenic sleep proves impossible, there is another option. It is older, simpler, and in some ways more terrifying. The generation ship. A generation ship is exactly what it sounds like, a spacecraft designed to travel for so long that multiple generations of humans are born, live, and die during the voyage. The people who depart Earth are not the people who arrive at the destination. Their children are not the ones who arrive, nor their grandchildren. Depending on the length of the journey, it could be dozens, hundreds, or even thousands of generations before the ship reaches its goal. The concept sounds almost medieval, like a floating village drifting through the void. And in many ways it is. A generation ship would need to be a self-sustaining world. It would need agriculture to produce food, systems to recycle water and air, manufacturing capability to repair and replace worn components, educational systems to pass knowledge from one generation to the next, medical facilities to maintain the health of the population, governance structures to resolve conflicts and make decisions, and cultural institutions to maintain social cohesion across centuries. One of the most critical questions is, how many people do you need? If the population is too small, genetic diversity becomes a problem. Inbreeding over many generations could lead to a genetic bottleneck, with deleterious mutations accumulating and the population becoming increasingly vulnerable to disease. Studies have estimated that a minimum viable population for a generation ship, one large enough to maintain genetic diversity over centuries, is somewhere between 10,000 and 40,000 individuals. Some more optimistic studies, using carefully managed breeding programs, have suggested that as few as 98 to 180 individuals might be sufficient. But this would require extraordinary discipline in reproductive choices, which raises profound ethical questions about individual freedom. The social and psychological challenges of a generation ship are perhaps even more daunting than the technical ones. The first generation, the ones who choose to leave Earth, will have a sense of purpose and mission. They will be volunteers, pioneers, driven by a dream. But their children, their grandchildren, the 10th generation, these people did not choose to be born on a spaceship. They did not volunteer for this mission. They are, in a very real sense, prisoners, born into a world they cannot leave, traveling toward a destination they will never see, because their ancestors made a choice for them. How do you maintain motivation across centuries? How do you prevent social collapse, revolution, or apathy? How do you preserve the knowledge and skills needed to complete the mission when the people who understood them have been dead for generations? These are not engineering problems. They are problems of human nature, and they are terrifyingly difficult. And yet, the generation ship may be the most realistic option for interstellar travel within the next few centuries. If our propulsion technology remains below 1 or 2% of light speed, the journey to the nearest star will take hundreds or thousands of years, and a generation ship may be the only way to do it. Project Hyperion, an international research initiative, is studying the feasibility of generation ships using current and near-future technologies. The challenges are immense, but they are not insurmountable. The third option is the most speculative and in some ways the most radical. What if instead of sending human bodies across the light year, we sent human minds? What if we could upload a human consciousness into a digital format, store it on a computer, and send that computer across interstellar space at high speed? A digital mind would not need food, water, or air. It would not need gravity. It would not need protection from radiation, at least not in the same way a biological body does. It could be stored compactly in a tiny spacecraft, and it could sleep for millennia without aging. At the destination, the digital minds could be downloaded into new bodies, perhaps grown from stored genetic material, or into robotic hosts, or into a virtual reality environment indistinguishable from the physical world. The idea is seductive, but the obstacles are mountainous. We do not understand consciousness. We do not know how the brain generates subjective experience. We cannot even define consciousness rigorously, let alone copy it. The human brain contains approximately 86 billion neurons, each connected to thousands of others by about 100 trillion synapses. Mapping this network at sufficient resolution, the so-called connectome, is a challenge that is currently beyond our technological capabilities, though projects like the Human Connectome Project are making progress. Even if we could map the brain completely, we do not know whether a digital copy of a brain would be conscious. Would it experience anything? Would it be you? Or would it be a philosophical zombie, a perfect simulation of you that behaves exactly like you, but has no inner experience? These are questions that touch on the deepest mysteries of consciousness and personal identity, and they do not have answers yet. But the possibility is tantalizing. If consciousness can be digitized, then the light-year problem becomes much more tractable. A tiny probe carrying a digital payload could be accelerated to high speeds with relatively little energy, cross the light-year barrier in years rather than centuries, and arrive at the destination with the minds of hundreds or thousands of people ready to be unpacked. Now, we have spent a long time discussing the challenges of crossing a light year with the technologies we have or could plausibly develop. But what about the technologies that live on the furthest edge of physics, the ones that might allow us to break the rules entirely? What about warp drives and wormholes? What about travelling faster than light? This is the question that everyone wants to ask, and the answer is both exciting and frustrating. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that sent shockwaves through the physics community. In it, he described a solution to Einstein's field equations of general relativity that allowed for effective faster-than-light travel. Not by moving an object through space faster than light, which is impossible, but by distorting space itself. The Alcubierre Warp Drive works like this. Imagine the spacecraft sitting in a bubble of flat spacetime. In front of the bubble, space is contracted, compressed, squeezed together. Behind the bubble, space is expanded, stretched out. The bubble, with the spacecraft inside, moves through space like a surfer on a wave. The spacecraft itself is not moving through space at all. Space is moving around it. And because it is space that is moving, not the spacecraft, there is no violation of the speed of light limit. The speed limit says that nothing can move through space faster than light. But it says nothing about space itself. Space can expand faster than light, and in fact, it already does in the distant reaches of the universe, where galaxies are being carried away from us by the expansion of the universe faster than light can travel between them. The Alcubierre drive is mathematically valid. It is a genuine solution to Einstein's equations, and it would, in principle, allow travel across a light year in any time you wanted, from years to days to hours to minutes. The speed of the warp bubble is not limited by the speed of light. But there are problems. Severe problems. First, the Alcubierre drive requires exotic matter, a substance with negative energy density. Normal matter has positive energy. Exotic matter would have negative energy, meaning it would gravitationally repel rather than attract. No such substance has ever been observed in macroscopic quantities. The Casimir effect, a quantum phenomenon where two closely spaced metal plates experience an attractive force due to quantum vacuum fluctuations, does produce a region of negative energy density between the plates, but the amount is vanishingly small, far too little to create a warp bubble. Second, the energy requirements of the original Alcubierre drive were staggering. Alcubierre himself estimated that the energy needed to create a warp bubble would be equivalent to the mass energy of the planet Jupiter. Later work by physicists like Chris van den Broek and others showed that the energy requirements could be reduced by optimizing the shape and thickness of the warp bubble. But even the most optimistic estimates still require enormous amounts of exotic matter and energy. Third, several physicists have identified potentially fatal problems with the warp drive concept. Some calculations suggest that the warp bubble would accumulate high-energy particles at its leading edge, releasing a devastating burst of radiation when the bubble collapsed. Others have shown that the interior of the warp bubble would be causally disconnected from the bubble's wall, meaning the occupants could not control the drive or even turn it off. And some analyses suggest that the warp bubble would be unstable, collapsing the moment it formed. Despite these challenges, research continues. In 2021, physicist Eric Lentz published a paper describing a class of warp drive solutions that might not require exotic matter at all, instead using a specific configuration of positive energy matter. The Applied Physics Group has also published work exploring physical configurations that could generate warp-like effects. These are very early results, and they are far from a proof of concept. But they suggest that the door to warp travel might not be completely closed. And then there are wormholes. Einstein-Rosen bridges. Shortcuts through the fabric of space-time. A wormhole is a hypothetical tunnel connecting two distant points in space-time. Imagine taking a sheet of paper and drawing 2 points on it, one at the top and one at the bottom. The distance between them along the surface of the paper might be, say, 20 centimeters. But if you fold the paper so that the 2 points are close together and then poke a hole through both layers, you create a shortcut, a connection that is much shorter than the surface distance. This is, very roughly, how a wormhole would work. It would connect two distant points in space, or even 2 points in time, through a higher dimensional shortcut. Wormholes are predicted by general relativity. They are mathematically valid solutions to Einstein's equations. But whether they actually exist, and whether they could be used for travel, are very different questions. The most commonly discussed type of traversable wormhole requires, once again, exotic matter with negative energy density to hold it open. Without exotic matter, the wormhole would collapse the moment anything tried to pass through it. The throat of the wormhole would squeeze shut faster than light, destroying anything inside. You would need to line the throat with exotic matter that pushes outward, counteracting the gravitational collapse and keeping the passage open long enough for a spacecraft to pass through. Kip Thorne, the Nobel Prize-winning physicist, did extensive work on traversable wormholes in the late 1980s, partly inspired by a request from Carl Sagan, who wanted a scientifically plausible faster-than-light travel mechanism for his novel Contact. Thorne showed that traversable wormholes are mathematically possible within general relativity, but require exotic matter whose existence remains unproven. If wormholes could be created, stabilized, and made large enough for a spacecraft to pass through, they would represent the ultimate solution to the light-year problem, not just for one light-year, but for any distance. You could step through a wormhole and emerge on the other side of the galaxy instantaneously. But this is so far beyond our current capabilities that it is, for all practical purposes, indistinguishable from magic. There have been other proposals for faster-than-light travel, and I want to mention a few of them briefly so that you understand the full landscape of what has been considered. Quantum entanglement is often cited as a potential mechanism for faster-than-light communication or travel. When two particles are entangled, measuring the state of one instantly determines the state of the other, regardless of the distance between them. This has been experimentally confirmed many times. But crucially, this does not transmit information faster than light. The results of entanglement measurements are random, and you cannot control what result you get. To extract information, you need to compare the results of both measurements, which requires a classical communication channel limited to the speed of light. Quantum entanglement is not a communication device, and certainly not a transportation device. Tachyons are hypothetical particles that always travel faster than light. They appear in some solutions to the equations of special relativity, but their properties would be exceedingly strange. A tachyon would have imaginary rest mass and would gain speed as it lost energy. No tachyon has ever been detected, and most physicists believe they do not exist. The M drive was a controversial concept for a reactionless thruster that appeared to produce thrust without expelling any propellant, apparently violating Newton's third law. Several research groups claimed to detect small amounts of thrust in experiments, leading to widespread media excitement. But subsequent, more careful experiments showed that the apparent thrust was an artifact of experimental error, thermal effects, and electromagnetic interference. Multiple independent tests have now failed to replicate the initial claims, and the physics community has largely concluded that the M drive does not work. So where does this leave us? The honest assessment is this. As of our best understanding of physics, the speed of light is an absolute limit for objects with mass. There may be loopholes, exotic solutions to Einstein's equations that allow for effective faster-than-light travel, but they all require physics that we do not currently possess and may never possess. The most realistic path to interstellar travel within the foreseeable future is to reach speeds of 5 to 20% of the speed of light using advanced propulsion systems like nuclear pulse, fusion, or laser sails. At these speeds, crossing 1 light-year takes 5 to 20 years, a timescale that is challenging but not impossible. And there is something profound in this. The universe has given us a speed limit, and that limit defines the character of our cosmic existence. We are not a species that can zip between the stars like gods. We are a species that must be patient, that must persist, that must plan on timescales that dwarf our individual lives. The light year is not just a unit of distance. It is a measure of our humility. Now, having explored the physics, the technology, the biology, and the dangers, let me bring everything together and give you the clearest, most comprehensive answer to our original question that I can. How many years would it take humanity to cross 1 light year? The answer depends entirely on what technology we use and when we attempt the crossing. So let me give you the answer in stages, because the truth is not a single number. It is a spectrum, a timeline, a story of human progress unfolding across centuries. If we launched a spacecraft today, right now, using our best available technology, the answer is approximately 1,560 years. That is the time it would take the Parker Solar Probe, the fastest human-made object in history, traveling at 692,000 kilometers per hour to cross 1 light year. To put that in perspective, 1,560 years ago, the Roman Empire had recently fallen in the West. The Middle Ages were just beginning. If someone had launched a spacecraft at Parker Solar Probe speed during the fall of Rome, it would be arriving at the 1 light year mark right about now. Think of everything that has happened in human history during that time. The rise and fall of the Byzantine Empire, the Islamic Golden Age, the Crusades, the Renaissance, the Reformation, the Scientific Revolution, the Industrial Revolution, 2 world wars, the space age, the digital revolution. All of that, all of human history from the fall of Rome to the present day, fits within the time our fastest spacecraft would need to cross 1 light year. And if we used a more typical fast spacecraft like Voyager 1 or New Horizons, the answer stretches to 17 to 18,000 years. That is nearly twice the length of recorded human civilization. From the first writing systems in Mesopotamia to the first TikTok video, approximately 5,000 years have passed. Multiply that by 3 or 4, and you have the time it would take Voyager to cross 1 light year. But those are today's numbers. What about tomorrow's? If, within the next 50 to 100 years, we develop nuclear pulse propulsion, an updated, modernized version of Project Orion, we could realistically achieve speeds of 3 to 5% of light speed. At 5% of light speed, crossing 1 light year takes about 20 years. That is within a single human career. An astronaut who departed at age 30 would arrive at 50. Still vigorous. Still capable. A 20-year mission is long by current standards, but it is not unprecedented. Long-duration submarines have operated for months without surfacing. Antarctic research stations keep personnel isolated for over a year. A 20-year interstellar mission would be an enormous challenge, but it is conceivable. If, by the mid to late 21st century, we achieve practical fusion propulsion, we could push speeds up to 10 to 15% of light speed. At 10%, 1 light year takes 10 years. At 15%, about 6.7 years, less than a decade. A journey that begins with children old enough to remember Earth and ends while they are still young adults. At these speeds, the nearest stars become reachable within a human generation. Proxima Centauri, at 25 light years, would take 28 to 42 years. A long voyage, but one that a person could undertake in middle age and complete in old age, or that a child could begin and an adult could finish. If in the 22nd or 23rd century we develop practical antimatter propulsion, the numbers become almost routine. At 50% of light speed, 1 light year takes 2 years. Alpha Centauri takes 8.5 years. At 70% of light speed, 1 light year takes about 1.4 years. And with time dilation, the subjective travel time would be even shorter. At 70% of light speed, the Lorentz factor is about 1.4, so the traveller would experience the 1 light year journey in about 1 year. At these speeds, interstellar travel starts to feel like what transoceanic voyages were in the 18th century. Long, dangerous, and demanding, but achievable. And if someday, perhaps in the far future, we develop something like a warp drive or discover how to create and stabilize traversable wormholes, the light-year barrier evaporates entirely. A warp drive could cross a light year in days, hours, or less. A wormhole could do it instantaneously. These technologies are purely speculative, and they may forever remain so. But they represent the ultimate ceiling of what is theoretically possible. So the answer to our question is not one number. It is a range, with today's technology, 1,560 to 18,000 years. With near-future nuclear technology, 20 years. With fusion technology, 7 to 10 years. With antimatter technology, 1 to 2 years. With speculative warp technology, days or less. And the difference between these numbers is not just a matter of engineering. It is a matter of civilizational ambition, political will, scientific investment, and, most of all, time. Given enough time, humanity can solve almost any engineering problem. The question is whether we will give ourselves that time, and this leads me to what I think is the most important dimension of this entire discussion. One that we have not yet touched, but that underlies everything we have talked about. It is not about physics or engineering, it is about us. About who we are as a species and what we choose to do with the time we have. Consider the trajectory of human technology over the past century. In 1903, the Wright brothers flew the first powered aircraft. A fragile wooden biplane that flew for 12 seconds and covered 37 meters. Just 66 years later, in 1969, human beings walked on the moon. In the span of a single human lifetime, we went from a wooden glider to the Sea of Tranquility. That is an acceleration of capability that is almost incomprehensible. In 1957, the Soviet Union launched Sputnik, the first artificial satellite. It was a polished metal sphere that did nothing but beep. Today, we have thousands of satellites in orbit, providing communication, navigation, weather forecasting, Earth observation, and scientific data. We have a permanently crewed space station. We have rovers on Mars. We have probes in interstellar space. We have a telescope orbiting the Sun 1 million miles from Earth that can see the first galaxies that formed after the Big Bang. In just 68 years, we went from a beeping metal ball to the James Webb Space Telescope. In 1945, the first nuclear fission weapon was detonated. Within a decade, we had nuclear power plants generating electricity. Within 2 decades, we had nuclear-powered submarines that could operate underwater for months without refueling. Within 3 decades, we were testing nuclear rocket engines under the Nerva program. The pace of nuclear technology development was extraordinary, and it was driven primarily by political will and funding. When the motivation was there, the technology followed. Now imagine this trajectory extended into the future. If we continue to advance at even a fraction of the rate we have maintained over the past century, the technologies we need for interstellar travel, fusion propulsion, advanced nuclear systems, laser arrays, perhaps even antimatter production, could be achievable within the next 100 to 300 years. That is not a long time. It is longer than any individual life, but it is a blink in the history of our species. And here is the thing that makes me most optimistic. We already know it can be done. We are not talking about violating the laws of physics. We are not talking about building impossible machines. We are talking about engineering challenges, about scaling up technologies that already exist in some form, about generating and concentrating energy, about building larger and more sophisticated systems. These are hard problems, incredibly hard, but they are solvable problems. The physics allows interstellar travel. The question is purely one of engineering, resources, and will. But there is a darker possibility that we need to acknowledge. We might not make it. Not because the physics is impossible, but because we might destroy ourselves before we get the chance. Climate change, nuclear war, engineered pandemics, artificial intelligence gone wrong, asteroid impacts. These are all existential risks that could end our civilization, or even our species, before we develop the technology to leave our solar system. The window of opportunity might be limited. We are a technologically advanced civilization, but we are also a fragile one, dependent on complex systems that could fail catastrophically. This is the deepest irony of the light-year problem. The same technology that could carry us to the stars, nuclear energy, advanced materials, artificial intelligence, could also destroy us if misused. The tools of salvation and the tools of destruction are, in many cases, the same tools. Our survival as a species depends not just on our technical ingenuity, but on our wisdom, our restraint, our ability to cooperate across national and cultural boundaries. Carl Sagan once said that we live on a mote of dust suspended in a sunbeam. Every human being who has ever existed, every king, every soldier, every lover, every child, every scientist, every poet, has lived and died on this tiny world. Our planet is a grain of sand on the beach of the cosmos, and the light year is the distance that separates our grain of sand from the next one. When you go outside tonight and look up at the stars, I want you to think about this. Each of those pinpoints of light is a sun, possibly with planets, possibly with life. And each one is separated from us by light years. The nearest one is 4.25 light years away, a distance that our fastest spacecraft would take 1,560 years to cross. The galaxy is 100,000 light years across. The nearest major galaxy is 2.5 million light years away. The observable universe is 93 billion light-years from edge to edge. We are surrounded by an ocean of distance so vast that it strains the very concept of vastness. And yet, we are not paralyzed by it. We are not defeated by it. We are challenged by it. We are inspired by it. We look at the light year and we do not see a prison wall. We see a frontier, a border waiting to be crossed, a mountain waiting to be climbed. And throughout our history, whenever we have encountered a frontier, a barrier, a seemingly impossible distance, we have eventually found a way across it. Our ancestors faced the oceans and saw an uncrossable void. They built boats and crossed them. Our ancestors faced the sky and saw an unreachable ceiling. They built aircraft and climbed through it. Our ancestors faced the vacuum of space and saw an impossible barrier. They built rockets and broke through it. And now we face the light year, the greatest distance any civilization has ever confronted. And I believe, with every fibre of my being, that we will cross it. Not because it is easy, not because it is guaranteed, but because it is who we are. We are the species that crosses frontiers. It is written into our DNA, into our history, into the very structure of our curiosity. The light year is not our enemy, it is our challenge, and challenges are what we were made for. Now I want to take you deeper into something that I think will completely reframe how you think about this problem, because so far we have been talking about crossing one light year as if it is a straightforward journey, just point A to point B, fly in a straight line and arrive. But the reality is far more complex and far more interesting than that. First, let us think about what it actually means to cross a light year. When we say we want to cross one light year, what are we really saying? Are we talking about a one-way trip or a round trip? Because the difference matters enormously. A one-way trip means you launch from Earth and you fly until you have covered 9.461 trillion kilometers. You arrive somewhere in deep space, one light year from where you started. But there is nothing there. One light year from Earth, in any direction, there is no star, no planet, no destination, just the cold, dark void of interstellar space. The nearest star, Proxima Centauri, is 4.25 light-years away. So crossing one light-year does not get you to a star. It gets you about a quarter of the way to the nearest star. You are stranded in the middle of the cosmic ocean, with no land in sight. So in a practical sense, crossing one light-year is not a useful mission by itself. The real question is whether we can cross the distance to the nearest star, which is 4.25 light-years. And that means multiplying all of our travel times by 4.25. Suddenly, the Parker Solar Probe's 1,560 years per light-year becomes 6,630 years to reach Proxima Centauri. Voyager 1's 17,500 years per light-year becomes 74,375 years. Even Project Orion's 20 years per light-year becomes 85 years to reach Proxima Centauri. And if you want to stop there, not just fly past, you need to decelerate as well, which roughly doubles the travel time, or requires even more fuel. And a round trip? Double everything again. A round trip to Proxima Centauri with Project Orion would take roughly 170 years, with fusion propulsion at 12% of light speed, roughly 70 years, with antimatter at 50% of light speed, roughly 17 years, with a laser sail at 20% of light speed, roughly 42 years, but remember, the laser sail has no way to decelerate, so it is a flyby only. These are sobering numbers, but they also contain a seed of hope, because they show that with technology only slightly beyond our current capabilities, we could potentially send a probe to the nearest star and receive data back within a century. That is long by human standards, but it is short by civilizational standards. Nations have existed for longer than that. Religions have endured for millennia. A 100-year interstellar probe mission is not unreasonable for a civilization that thinks in centuries rather than election cycles. Second, let us think about what you would actually see during a journey across one light year. Most people imagine that traveling through space would be boring, just darkness and stars for years on end. And at low speeds, that is largely true. But at relativistic speeds, things get much more interesting and much weirder. As a spacecraft accelerates to significant fractions of light speed, several bizarre relativistic effects become apparent. The first is aberration. The stars in the forward direction appear to crowd together, bunching up in front of the ship. Stars that would normally be spread across the sky migrate toward the forward direction, as if the entire universe is funneling into a point ahead of you. Behind the ship, the stars spread apart and become more sparse. The universe looks like it is being stretched behind you and compressed in front of you. The second effect is the Doppler shift. Stars ahead of the ship are blue shifted, their light compressed to shorter wavelengths. They appear bluer, and eventually, as you go faster, their visible light shifts into the ultraviolet and then into the X-ray range, becoming invisible to the naked eye, but potentially dangerous as high-energy radiation. Stars behind you are redshifted, their light stretched to longer wavelengths. They appear redder, then shift into the infrared, and eventually become invisible. The third effect is the headlight effect. Because of the way relativity alters the distribution of light, the forward hemisphere becomes much brighter than the rear hemisphere. More light is concentrated in the forward direction, and less in the rear. At very high speeds, almost all the light you see comes from directly ahead, creating a brilliant blue-white spotlight in the direction of travel, surrounded by a gradually darkening sky that fades to complete blackness behind you. The fourth effect is time dilation, which we have already discussed. At high speeds, time passes more slowly for you. If you are traveling at 90% of light speed and you look at a clock on a planet you are passing, you would see it ticking faster than yours. The universe around you is aging more quickly than you are. Events that take years in the outside world are compressed into months or weeks or days from your perspective. And the fifth effect is length contraction. In the direction of motion, distances are compressed. The light year that you are crossing is not, from your perspective, 9,461 trillion kilometers long. At 90% of light speed, it appears to be only about 4.12 trillion kilometers long. At 99%, it appears to be about 1.34 trillion kilometers. The faster you go, the shorter the distance becomes from your point of view. This is not an illusion. It is a real physical effect, a consequence of the geometry of space-time at relativistic speeds. The universe literally shrinks in your direction of travel. These effects combine to create a visual experience that would be utterly unlike anything any human being has ever seen. Flying across a light year at relativistic speed would be a psychedelic, mind-bending, almost hallucinatory experience. The familiar night sky would be transformed into something alien and terrifying and beautiful. The stars would flow around you like a river of light, concentrating into a blazing point ahead and fading into darkness behind. You would be witness to the deepest structure of space-time itself, made visible by your own velocity. And this brings me to another aspect of interstellar travel that is often overlooked. Navigation. How do you steer a spacecraft across a light year? Within our solar system, navigation is relatively straightforward. We have precise maps of every planet, moon, asteroid, and comet. We have radio beacons on Earth that can transmit signals to spacecraft and receive signals back, allowing us to track their positions with extraordinary accuracy. We can make course corrections based on real-time data. But in interstellar space, none of this works. Earth's radio beacons are too far away for precise navigation, and the signal delay is measured in years. There are no landmarks, no beacons, no GPS satellites. The spacecraft must navigate autonomously, using whatever reference points it can find. The most promising solution is pulsar navigation. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation. As they spin, these beams sweep across space like lighthouse beacons. Each pulsar has a unique rotation period, and many pulsars are extraordinarily precise timekeepers, rivaling the best atomic clocks on Earth. By measuring the arrival times of signals from multiple pulsars, a spacecraft could triangulate its position with remarkable accuracy, much like GPS uses signals from multiple satellites. The concept is not just theoretical. NASA has already tested a version of pulsar navigation called Sextant, the station explorer for X-ray timing and navigation technology, on the International Space Station. Sextant uses X-ray emissions from pulsars to determine position, and it has demonstrated accuracy to within a few kilometers. For an interstellar spacecraft, pulsar navigation could provide continuous, autonomous position fixes throughout the entire journey, without any communication with Earth. But there is a subtlety. At relativistic speeds, the signals from pulsars would be affected by the same aberration and Doppler effects that alter the starlight. The navigation system would need to account for these effects, correcting for the compression and frequency shifting of the pulsar signals. This is a solvable problem, but it adds complexity to an already complex system. There is also the question of obstacle avoidance. As we discussed earlier, the interstellar medium is not empty. There are dust grains, gas clouds, rogue planets, brown dwarfs, and other objects scattered through space. At relativistic speeds, even small objects are deadly. The spacecraft would need some form of forward detection system, perhaps a powerful radar or LiDAR, that could identify objects in the ship's path and trigger evasive maneuvers or activate protective shields. But detection at relativistic speeds is itself a challenge. If you are traveling at 20% of light speed and you detect an object 1 light hour ahead, you have about 5 hours to react. That sounds like a lot, but at 20% of light speed, even a slight course change requires enormous energy, and the spacecraft's momentum makes rapid maneuvering difficult. At 50% of light speed, you would have less than 2 hours. At 90%, the situation becomes nearly impossible for anything but the smallest adjustments. This is one of the reasons why some interstellar travel concepts envision sending a stream of tiny expendable probes ahead of the main spacecraft, like scouts clearing a path through a minefield. These probes would detect hazards and either remove them or map a safe route for the main vessel to follow. It is an expensive and complex approach, but it might be necessary for safe travel at relativistic speeds. Now, I want to address something that has been lurking beneath the surface of this entire discussion. Something that I think makes this question more than just a scientific curiosity. It makes it existential. The question of whether humanity can cross a light year is really the question of whether we are alone, or whether we can discover that we are not. The nearest star, Proxima Centauri, has at least 2 confirmed planets. One of them, Proxima Centauri b, orbits in the habitable zone, the region around a star where temperatures could allow liquid water to exist on a planet's surface. This does not mean that Proxima b has life. We know very little about its atmosphere, its geology, or its conditions. It might be a frozen wasteland. It might be a barren rock. It might be shrouded in a toxic atmosphere that would kill any Earth-based organism in seconds. But it might, just possibly, have life. Or the conditions for life. Or the remnants of life. And Proxima Centauri is just one star. The Milky Way galaxy contains between 100 and 400 billion stars. Current estimates suggest that there are roughly as many planets as stars, possibly more. That means there could be hundreds of billions of planets in our galaxy alone. And the observable universe contains roughly 2 trillion galaxies. The total number of planets in the observable universe is almost certainly in the trillions of trillions. The scale is incomprehensible.